Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin, take a moment to get comfortable. Adjust your pillow, let your body sink into wherever you're resting, and know that for the next couple of hours, there's nowhere else you need to be. Where in the world are you watching from? A quiet bedroom as the day finally winds down? A cosy corner where the stars might be visible through your window? Wherever you are, you're welcome here. Tonight we're going to explore something extraordinary that happened in our cosmic neighbourhood, and a question that captures both wonder and worry in equal measure. We'll discover what happens when objects from beyond our solar system come calling, understand what these interstellar visitors tell us about the universe, and contemplate what it might mean if one of them had Earth's name on it. We're going to look at two I/Borisov, Oumuamua, and the fascinating, slightly unsettling question. What's the worst-case scenario for our planet? But don't worry, this isn't going to be a doomsday countdown or a breathless race against cosmic catastrophe. Instead, we'll move slowly and carefully through the science, the statistics, and the genuine scenarios that astronomers actually think about. By the end, I think you'll find that while the universe is vast and sometimes unpredictable, there's something deeply peaceful in understanding our place within it, and the incredibly low odds of catastrophe. If you enjoy these calm explorations of space and science, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being part of this community of curious minds who like to fall asleep learning something new, so settle in. Let your shoulders drop away from your ears. Take a slow breath in through your nose and let it out gently. And let's begin our slow drift through the cosmos, where visitors from distant stars occasionally pass by, and where Earth continues its patient orbit around our Sun, safe and serene. There's no urgency here. Just listen, and let the story unfold like the gentle expansion of space itself. On August 30th, 2019, a Ukrainian amateur astronomer named Gennady Borisov was doing what he loved to do on clear nights, scanning the sky with his homemade telescope. He had built the instrument himself, a 0.65 metre reflector, and he used it to search for comets, those beautiful wanderers of our solar system. But on this particular night, he found something that would change our understanding of how often the universe sends messengers from beyond our cosmic doorstep. He noticed a small, fuzzy object moving against the background of stars. At first, it seemed like it might be just another comet, perhaps one in a long elliptical orbit around our Sun. But as he and other astronomers tracked it over the following days, something remarkable became clear. The object was moving too fast, and its trajectory was all wrong. It wasn't orbiting our Sun at all. It was just passing through. This visitor from interstellar space would eventually be designated 2I/Borisov, meaning it was the second interstellar object ever detected. The I stands for interstellar, a category that had been created just 2 years earlier for the first such visitor, Oumuamua. Borisov had discovered something that, until very recently, astronomers had only theorized about. Proof that objects from other star systems regularly pass through our solar neighbourhood. The comet was roughly half a mile across, tumbling through space at about 110,000 miles per hour relative to our Sun. But what made it truly special wasn't just where it came from, but what it told us. Unlike Oumuamua, which had been small, dark and cigar-shaped, raising all sorts of questions about its nature, 2I/Borisov looked exactly like a comet. It had a tail, it was shedding gas and dust, it behaved in predictable ways. It was, in essence, a normal comet that just happened to come from somewhere else. This normality was actually quite profound. It suggested that the building blocks of planetary systems, the icy chunks and rocky fragments that orbit other stars, aren't all that different from the ones in our own solar system. The universe, it seemed, uses similar ingredients wherever you go. Water ice, carbon compounds, silicate dust. These materials appear to be universal. As 2I/Borisov made its closest approach to our Sun, In December 2019, coming within about 190 million miles, telescopes around the world and in space turned to observe it. The Hubble Space Telescope captured detailed images. Ground-based observatories analysed its composition. Scientists studied how it released gas, how fast it was spinning, what it was made of. They were essentially getting a sample of another planetary system delivered right to their instruments, and they weren't going to waste the opportunity. The comet's journey through our solar system would be brief. By mid-2020, it had already passed beyond the orbit of Mars on its way back out into interstellar space. It came from somewhere in the direction of Cassiopeia, though we can't trace its path back to any specific star. It will drift through the galaxy for millions or billions of years, perhaps eventually encountering another planetary system, another sun, another chance to be observed by curious minds. To understand why 2I/Borisov mattered so much, we need to go back 2 years earlier, to October 2017. When astronomers discovered something that would make them completely rethink how they classified celestial objects. A telescope in Hawaii called Pan-STARRS-1, part of a system designed to scan the sky for near-Earth asteroids and other potentially hazardous objects, detected something unusual moving through the inner solar system. The object was designated A/2 017U1 at first, the Statistical Oumuamua, standing for asteroid. But as astronomers calculated its orbit, they realised something extraordinary. It was moving on a hyperbolic trajectory, meaning it had come from interstellar space and was travelling fast enough to escape the sun's gravity. It would pass through our solar system once and never return. It wasn't ours, it was just visiting. This was the first time humanity had detected an object that definitively came from another star system. The discovery was so significant that the International Astronomical Union created a new classification just for it, "2" for interstellar. The object was renamed 1I/2017U1, and later given the name Oumuamua, a Hawaiian word meaning scout, or messenger from afar arriving first. Oumuamua was strange in ways that 2I/Borisov wasn't. It was elongated, shaped something like a cigar or perhaps a pancake, depending on who you asked. It measured about 400 metres long, but only about 40 metres wide. It was tumbling through space, rotating about once every 7 hours, and it was dark, very dark, reflecting only about as much light as a heavily weathered asteroid. As it tumbled past Earth's orbit and around the Sun, Oumuamua did something unexpected. It accelerated slightly, as if something was pushing it. Comets do this all the time. When they get close to the Sun, ice on their surface vaporizes, creating jets of gas that can act like tiny rocket engines. But Oumuamua showed no signs of outgassing, no tail, no coma of gas and dust. It looked like an asteroid, but it was behaving, just slightly, like a comet. This discrepancy led to all sorts of speculation. Some scientists suggested it might be covered in a layer of organic compounds that had been darkened by cosmic radiation, and beneath that layer was pristine ice that vaporized without creating a visible tail. Others proposed it could be made of hydrogen ice, which would be transparent and wouldn't create a dusty tail, and a few, most notably Harvard astronomer Avi Loeb, suggested it could be an artificial object, perhaps a light sail from an alien civilization. The alien hypothesis captured public imagination, but most astronomers remained skeptical. The universe is strange enough without needing to invoke extraterrestrial technology. Natural explanations, while sometimes exotic, are usually more likely. But the debate highlighted something important. We had only detected one interstellar object, and we didn't have enough data to fully understand it. We needed more examples. By the time astronomers realised what they had found, Oumuamua was already on its way out of the solar system. It had reached its closest point to the Sun on September the 9th, 2017, more than a month before anyone knew it was there. By the time it was discovered on October 19th, it was already racing away. Telescopes around the world tried to gather as much data as possible before it faded from view, but there was only so much they could learn from an object that was quickly becoming too faint to observe. Oumuamua is now somewhere beyond Neptune's orbit, heading out into the vast darkness between stars at about 58,000 miles per hour relative to the Sun. In about 20,000 years, it will pass within a few light years of the star Ross 154. After that, it will continue its lonely journey through the galaxy, perhaps for billions of years, carrying with it the mystery of its origin. After the discovery of Oumuamua and then 2I/Borisov, astronomers began to ask a question that was both scientific and slightly eerie. How often do objects from other star systems pass through our solar system? And perhaps more importantly, how many have we missed? The answer, it turns out, is that interstellar visitors are probably quite common. We just haven't been looking for them until recently, and they're incredibly hard to spot. Think about it this way. Space is vast. And even our solar system, which feels enormous to us, is mostly empty space. An object the size of Oumuamua, even if it passed relatively close to Earth, would appear as nothing more than a faint dot moving against the background stars. Astronomers have run the numbers, and their estimates are fascinating. Based on the rate at which we've discovered interstellar objects with current telescopes, they calculate that at any given moment there might be thousands of interstellar objects passing through the solar system. Most of them are probably quite small, chunks of rock or ice no bigger than a car or a house. They zip through, completely unnoticed, and continue on their way. Larger objects like Oumuamua and 2I/Borisov are rarer but still not uncommon. Scientists estimate that objects about the size of Oumuamua pass through the inner solar system perhaps once or twice a year. Larger objects the size of mountains or small asteroids might pass through once every few decades or centuries, and truly massive objects, kilometres across, might venture through the solar system only once every few thousand or million years. These estimates are based on models of how planetary systems form and how often they eject material into interstellar space. When a star system is young and its planets are still taking shape, gravitational interactions can fling countless objects outward. Jupiter, for instance, has probably ejected millions of comets from our solar system over the past 4 billion years. Other star systems do the same thing. The galaxy is full of these cosmic refugees, wandering between the stars. The Milky Way galaxy contains somewhere between 100 and 400 billion stars, and many of those stars have planetary systems. Even if only a tiny fraction of those systems eject objects into interstellar space, the sheer number of stars means the galaxy should be full of wandering rocks and icebergs. Our solar system, from this perspective, sits in a slow-motion blizzard of interstellar debris. But here's the thing that's both reassuring and slightly strange to contemplate. We're only now developing the technology to see this blizzard. The Pan-STARRS telescope that discovered Oumuamua came online in 2010. Before that, we simply didn't have systematic surveys sensitive enough to catch these fast-moving visitors. There could have been a dozen interstellar objects that passed through the inner solar system in the 20th century, and we would never have known. This realization has spurred investment in better sky surveys. The Vera C. Rubin Observatory, scheduled to begin operations in the mid-2020s, will scan the entire visible sky every few nights. It's expected to discover dozens, possibly hundreds of interstellar objects. We'll finally get a clear picture of just how common these visitors are, what they're made of, and where they come from. And this is where the question starts to form, the one that we're here to explore slowly and carefully. If interstellar objects are passing through our solar system all the time, some of them quite large, what happens if one of them is on a collision course with Earth? What's the worst-case scenario? Before we can understand what would happen if an interstellar object hit Earth, we need to understand what these objects actually are. And the truth is, based on our sample size of 2, they seem to be quite diverse. Let's start with 2I/Borisov, the one we understand better. It was, in almost every way, a normal comet. Comets are essentially dirty snowballs. chunks of ice mixed with dust and rocky material. When they get close to a star, the ice begins to vaporize, creating a glowing cloud of gas called a coma, and often a tail that points away from the star due to solar wind and radiation pressure. Analysis of 2I/Borisov showed it was rich in carbon monoxide, more so than most comets in our solar system. This suggests it formed in a very cold environment, probably in the outer regions of its home star system. It also contained water ice, cyanide compounds, and various organic molecules. In composition, it wasn't all that different from the comets that formed around our own Sun 4.5 billion years ago. The comet's size was estimated at roughly 500 to 700 metres across, about half a mile. That's substantial, but not enormous by cosmic standards. For comparison, Halley's Comet, the famous periodic visitor to Earth's skies, is about 15 kilometres long. 2I/Borisov was a modest comet, unremarkable except for the fact that it came from another star. Oumuamua, on the other hand, remains mysterious. Its elongated shape was unusual but not unheard of. Some asteroids in our solar system have similar shapes, possibly the result of being fragments from larger objects that broke apart. Its dark colour suggested it was covered in organic compounds that had been irradiated by cosmic rays over millions or billions of years of travel through interstellar space. The strangest thing about Oumuamua was its slight acceleration as it left the solar system. The best explanation, favoured by most astronomers, is that it was outgassing like a comet, but in a way that didn't produce a visible tail. Perhaps the gas was being released from just one side, or perhaps the material vaporizing was something that doesn't create dust, like pure nitrogen or hydrogen ice. We simply don't know for certain. What we can say is that interstellar objects, like objects in our own solar system, probably come in a wide variety of forms. Some are icy comets, some are rocky asteroids, some might be fragments from planetary collisions, chunks of crust or mantle blasted into space by ancient impacts. Some might be rich in metals, pieces of the cores of destroyed protoplanets. The universe has been making and breaking worlds for billions of years, and all that debris has to go somewhere. One interesting possibility is that some interstellar objects might be relics from the very early universe, from a time when stars were just beginning to form. These objects could contain pristine material from the epoch of planet formation, material that has been preserved in the freezing cold of interstellar space. Studying them would be like opening a time capsule from the dawn of planetary systems. Another possibility that fascinates scientists is that some interstellar objects might carry organic compounds, or even simple microorganisms. If life exists elsewhere in the galaxy, and if it can survive the harsh radiation and cold of interstellar space in a dormant state, then these wandering rocks could be spreading life from star to star. This idea, called panspermia, is speculative but not impossible. We know that some Earth microorganisms can survive in extreme conditions, including the vacuum of space for short periods. But whether they're icy comets, rocky asteroids, or something more exotic, all interstellar objects share one characteristic. They're travelling at high speed. Because they're not bound by the sun's gravity, they're moving much faster than typical solar system objects. And speed, as we'll explore, matters a great deal when we start thinking about impacts. To understand what would happen if an interstellar object struck Earth, we need to talk about velocity, because velocity is what determines the devastating power of an impact. And interstellar objects, by definition, are moving fast. Objects in our solar system that orbit the Sun have velocities that are, while impressive to us, relatively modest by cosmic standards. Earth, for instance, orbits the Sun at about 30 kilometers per second, or roughly 67,000 miles per hour. That sounds fast, and it is, but it's nothing compared to interstellar velocities. When an object enters our solar system from interstellar space, it typically has a velocity of at least 26 kilometers per second, which is the speed needed to escape the Sun's gravity from Earth's distance. That's the minimum. Many interstellar objects are moving faster, sometimes much faster. Oumuamua, for example, was clocking about 26 kilometers per second when it entered the solar system, but its velocity relative to the Sun increased as it fell toward the Sun and then decreased as it climbed back out. 2I/Borisov was moving at about 32 kilometers per second relative to the Sun when it was first discovered. That's about 72,000 miles per hour. And these are actually on the slower end of what's possible. Some interstellar objects could be moving at 50 or even 100 kilometers per second, especially if they were ejected from their home systems by close encounters with massive planets or stars. Now let's think about what happens when a fast-moving object hits a planet. The energy of an impact depends on two things: the mass of the object and the square of its velocity. That last part is important. Double the velocity and you quadruple the energy. Triple the velocity and you increase the energy ninefold. When astronomers talk about asteroid impacts on Earth, they usually think about objects that are already orbiting the Sun. These objects, if they hit Earth, would strike at relative velocities between 11 and 72 kilometers per second, depending on the angle and direction of approach. An asteroid coming from the outer solar system, approaching Earth head-on, could hit at the upper end of that range. An asteroid that Earth essentially catches up to would hit at the lower end. But an interstellar object isn't orbiting the Sun. It's just passing through. And depending on the geometry of the encounter, it could hit Earth at velocities well over 100 kilometers per second if it was approaching the solar system head-on and Earth happened to be in its path. At those speeds, the kinetic energy of even a relatively small object becomes enormous. Let's put some numbers to this just to make it concrete. Imagine an interstellar asteroid about 500 meters across, similar in size to 2I/Borisov. Let's say it's made of rock with a density similar to granite. Such an object would have a mass of about 200 million tons. Now let's say it hits Earth at 80 kilometers per second, a plausible velocity for an interstellar impact. The kinetic energy of that impact would be about 640 megatons of TNT equivalent. For comparison, the largest nuclear weapon ever tested, the Soviet Tsar bomber, released about 50 megatons. So we're talking about an impact with the energy of more than a dozen of the largest hydrogen bombs ever built, all going off at once in the same spot. Such an impact would create a crater perhaps 5 to 10 kilometers across. If it hit on land, it would devastate an area the size of a large city and surrounding suburbs. If it hit in the ocean, it would create tsunamis that could inundate coastal areas for hundreds of miles. The dust and debris thrown into the atmosphere could affect climate for months or even years, depending on where it struck and what it hit. That sounds catastrophic, and it would be, certainly on a regional scale. But here's the thing we need to keep in perspective, and we'll return to this thought throughout our exploration. Earth is big, and space is bigger. The odds of an interstellar object hitting Earth at all are vanishingly small, and even if one did, it would most likely hit ocean or unpopulated land. The worst-case scenario, while worth understanding, is also extraordinarily unlikely. There's something both beautiful and terrifying about the mathematics of planetary collisions, something that reveals just how protected we are by the sheer vastness of space, even as it shows us how vulnerable we might be if the numbers ever align against us. Let's start with the basics. Earth is a sphere with a diameter of about 12,742 kilometers. That's big enough to walk around for months without retracing your steps, big enough to contain vast oceans and continents, big enough that it feels infinite when you're standing on its surface looking at the horizon. But from the perspective of space, Earth is tiny. Imagine, if you will, a disk the size of Earth sitting in the vastness of the solar system. That disk has an area of about 127 million square kilometers. Sounds like a lot, doesn't it? But now consider that the area of a sphere with a radius of Earth's orbit around the Sun, what we call an astronomical unit, is about 2.8 trillion square kilometers. Earth's cross-section, the target that an incoming object has to hit, is 0.0000045% of that area. Put another way, if you randomly threw a dart at a sphere the size of Earth's orbit, the chance of hitting Earth would be about 1 in 22 million. And that's assuming the dart was perfectly aimed at the orbital plane of Earth. If the dart could come from any direction in three-dimensional space, the odds get even worse. But of course, space isn't a dartboard, and interstellar objects aren't being aimed at us. They're following trajectories determined by where they came from and how they were moving when they entered the solar system. Most of them never come anywhere near Earth's orbital distance from the Sun. They might pass through the outer solar system, barely perturbed by the Sun's gravity, and continue on their way. Or they might plunge close to the Sun and then head back out, crossing Earth's orbital path but doing so when Earth is on the other side of its orbit. The probability of a collision depends on many factors: the trajectory of the incoming object, its velocity, the gravitational pull of the Sun and planets, and pure chance regarding where Earth happens to be in its orbit. Astronomers can calculate these probabilities, and they've done so for various scenarios. For objects the size of 2I/Borisov, roughly half a kilometre across, passing through the inner solar system, the probability of striking Earth on any given pass is something like 1 in several billion. Multiply that by the estimated rate at which such objects pass through, perhaps 1 or 2 per year, and you get a collision probability of perhaps 1 every few billion years. Smaller objects are more common, but they also represent less danger. An interstellar boulder the size of a house might pass through the solar system every few months, but the odds of it hitting Earth are still astronomical. And if it did hit, it would likely burn up in the atmosphere, creating a spectacular fireball, but no damage on the ground. Larger objects, the size of mountains or small asteroids, are rarer. They might pass through once every few thousand years, but when you combine their rarity with the low probability of collision, you end up with events that might occur once every few tens or hundreds of millions of years. The mathematics, in other words, is on our side. Earth has been orbiting the Sun for 4.5 billion years, and in all that time we have no clear evidence of an interstellar impact. That doesn't mean it's never happened, but it does suggest such events are rare enough that they haven't noticeably affected Earth's geological or biological history. This is worth contemplating as we continue our exploration. The universe is not actively hostile to us. It's simply indifferent, operating according to the laws of physics and probability. And those laws, those probabilities, lean heavily in favour of Earth remaining unscathed by interstellar visitors. While we haven't detected any confirmed interstellar impacts on Earth, we have a rich history of impacts from solar system objects, asteroids and comets that were already orbiting the Sun. These events, both recent and ancient, teach us a great deal about what to expect if an interstellar object ever did strike our planet. The most famous impact in recent history, though, quote 5 Gyung here means 66 million years ago, was the Chicxulub impact that helped bring about the extinction of the dinosaurs. An asteroid roughly 10 kilometers across struck what is now the Yucatan Peninsula in Mexico, creating a crater 150 kilometers wide and releasing energy equivalent to about 100 million megatons of TNT. The impact itself was devastating on a global scale. The immediate effects included earthquakes that would have registered magnitude 10 or 11, tsunamis hundreds of meters high that swept across shallow seas, and a blast wave that levelled forests thousands of kilometres away. But it was the long-term effects that made this impact truly catastrophic. Dust and debris thrown into the upper atmosphere blocked out the sun for months, or possibly years, causing global cooling and the collapse of photosynthesis-based food chains. About 75% of all species on Earth went extinct in the aftermath. The dinosaurs, except for their bird descendants, disappeared. Many marine species vanished. Entire ecosystems collapsed. The world that emerged from the ashes of the Chicxulub impact was fundamentally different from the one that existed before. But here's an important point to remember. The Chicxulub impactor was enormous, far larger than any interstellar object we've detected so far. Objects that size, whether from our solar system or from interstellar space, are incredibly rare. The average time between Chicxulub-scale impacts is estimated at 50 to 100 million years. More recent impacts have been smaller and more instructive about what we might expect from something like Borisov. In 1908, an object estimated to be about 50 to 60 meters across exploded over Tunguska in Siberia. It didn't actually hit the ground. It detonated in the atmosphere, but the airburst released energy equivalent to about 10 to 15 megatons of TNT. The explosion flattened about 2,000 square kilometers of forest, knocking down an estimated 80 million trees in a radial pattern centered on the blast. If the Tunguska event had occurred over a city instead of a remote wilderness, it would have killed thousands or possibly millions of people, but it didn't, precisely because most of Earth's surface is not densely populated. The ocean covers 71% of our planet. Of the remaining land, much is uninhabited or sparsely populated. The odds of an impact occurring in a densely populated area are again quite low. Even more recently, in 2013, a meteor about 20 meters across entered Earth's atmosphere over Chelyabinsk, Russia. It exploded at an altitude of about 30 kilometers, creating a shock wave that shattered windows and damaged buildings across a wide area. About 1,500 people were injured, mostly by flying glass. The energy released was about 500 kilotons, roughly 30 times the energy of the Hiroshima atomic bomb. The Chelyabinsk meteor was smaller than anything we'd worry about from an interstellar visitor, but it demonstrated something important. Even relatively small impacts can cause significant damage if they occur over populated areas. It also showed us that Earth's atmosphere provides substantial protection. The meteor was destroyed by atmospheric entry. It didn't reach the ground intact. For an interstellar object like I/Borisov, which is much larger, atmospheric entry would be different. An object 500 meters across moving at 80 kilometers per second would punch through the atmosphere in just seconds, losing relatively little velocity to atmospheric drag. It would hit the ground with most of its kinetic energy intact, creating that crater we discussed earlier, 5 to 10 kilometers across. But again, let's keep perspective. The Chicxulub impact, devastating as it was, required an object 20 times larger than Borisov. The Tunguska event was caused by something 10 times smaller. The range of possible impacts is vast, and the truly catastrophic ones, the civilization-ending or species-ending events, require objects that are both large and rare. One of the more unsettling aspects of interstellar objects is how little warning we'd have if one were headed our way. Both Oumuamua and I/Borisov were detected only after they had already entered the inner solar system, and Oumuamua wasn't even found until it was already leaving. This raises an important question. Could we detect an Earth-threatening interstellar object in time to do anything about it? The short answer is maybe, but it depends. Current sky surveys like Pan-STARRS, the Catalina Sky Survey, and the upcoming Vera C. Rubin Observatory are designed primarily to detect near-Earth asteroids, objects that are already in our solar system and might pose a threat to Earth. They're getting better at detecting interstellar objects as a bonus, but these visitors present unique challenges. First, interstellar objects are moving faster than solar system objects. This means they spend less time in the inner solar system where our telescopes can see them. An asteroid in an elliptical orbit around the Sun might take months or years to cross through the region where it's bright enough to detect. An interstellar object might zip through that same region in weeks. Second, we don't know where to look. Near-Earth asteroids tend to be found in predictable regions of sky because they are orbiting the Sun in a regular pattern. Interstellar objects can come from any direction. Detecting them requires all sky surveys that repeatedly scan the entire visible sky, and such surveys are resource-intensive and limited by current technology. Third, many interstellar objects might be quite dark. If they're covered in organic compounds that have been darkened by cosmic radiation, like Oumuamua appeared to be, they reflect very little sunlight. A dark object moving fast is about the hardest thing to detect in space. Let's imagine a scenario. An interstellar object, similar in size to 2I/Borisov, is approaching the solar system on a trajectory that will bring it very close to Earth. How much warning would we have? If the object is detected when it crosses the orbit of Jupiter, roughly 5 astronomical units from the Sun, we might have several weeks to a few months of warning, depending on its exact trajectory and velocity. That sounds like a lot of time, but remember, we'd need to first detect the object, then track it long enough to calculate a precise orbit, then determine if it actually poses a threat to Earth, and then decide what, if anything, could be done. If the object isn't detected until it crosses the orbit of Mars, less than 2 astronomical units from the Sun, we might have only days or weeks. At that point, options become extremely limited. There's no time to launch a spacecraft to deflect it, no time to evacuate large populations from threatened areas if we knew where it would strike. The reality is that our current detection capabilities give us pretty good coverage for large objects approaching from certain directions, but there are blind spots. An object approaching from the direction of the Sun, for instance, would be nearly impossible to detect until it had already passed us. Telescopes can't look directly at the Sun without being overwhelmed by its brightness. This is why space agencies around the world are investing in better detection systems. NASA's Planetary Defense Coordination Office, established in 2016, coordinates efforts to detect and track near-Earth objects. The European Space Agency has similar programs. These efforts are primarily focused on solar system objects, but they'll also catch interstellar visitors as a side benefit. The Vera C. Rubin Observatory, when it begins operations, will be a game changer. It will scan the entire visible sky every few nights, detecting objects much fainter and farther away than current surveys can see. It should catch most large interstellar objects while they're still well outside Earth's orbit, giving us maximum warning time. But even with perfect detection, there's the question of what we could actually do about an incoming threat. Deflecting an asteroid is hard enough when you have years of warning and the object is in a predictable orbit. Deflecting an interstellar object moving at 80 kilometers per second with only weeks or months of warning might be beyond our current capabilities. This is sobering to think about, but it's also important to remember the context. The probability of such an event is extremely low. We're talking about preparing for something that might happen once every few billion years. It's worth thinking about, worth preparing for to the extent we can, but not worth losing sleep over. So far, we've been talking about relatively small interstellar objects, things the size of 2I/Borisov or even a bit larger. But the worst-case scenarios that keep some astronomers up at night involve something much, much bigger. A rogue planet. Rogue planets, also called free-floating planets or orphan planets, are worlds that have been ejected from their home star systems and now wander through interstellar space. They don't orbit any star. They're just drifting through the galaxy, cold and dark and alone. We know these objects exist. Astronomers have detected several dozen candidates through various methods, though confirming them as actual planets rather than failed stars called brown dwarfs can be tricky. The leading theories of planet formation suggest that rogue planets should be quite common, possibly outnumbering stars in the galaxy. When planetary systems form, gravitational interactions between planets can fling some of them outward into interstellar space. Most rogue planets are probably Jupiter-sized or smaller, a gas giant that formed in the outer regions of a planetary system and then got ejected by gravitational interactions with other planets. But there could also be rocky planets, Earth-sized or even larger, wandering between the stars. Now, imagine that one of these rogue planets, let's say something the size of Mars, happened to pass through our solar system. The odds are overwhelmingly against it actually hitting Earth, but let's think about what would happen if it did, just to understand the absolute worst case. An impact with a Mars-sized object would be, in a word, apocalyptic. Mars has a diameter of about 6,800 kilometers, roughly half the diameter of Earth, but it has about 11% of Earth's mass. If such an object struck Earth at interstellar velocities, the kinetic energy released would be almost beyond comprehension. The impact would likely vaporize both the rogue planet and a significant portion of Earth. The collision would release enough energy to melt the Earth's crust, possibly down to the mantle. The planet would be reshaped entirely. The oceans would boil away. The atmosphere would be blown into space or transformed into a toxic soup of vaporized rock. Any life on Earth would be extinguished instantly within thousands of kilometers of the impact point, and within hours or days everywhere else as the planet was engulfed in a global firestorm. The Earth that emerged from such a collision, if it remained a cohesive body at all, would be a molten hellscape, completely uninhabitable. This is the worst-case scenario, the absolute extreme of what could happen. It's the kind of event that would not only end human civilization, but potentially reset the entire evolution of life on Earth, assuming any life survived at all. But let's immediately put this in perspective. The probability of such an event is so low that it's almost not worth calculating. For a rogue planet to hit Earth, it would have to be heading directly toward our solar system, passing through the exact region of space where Earth happens to be in its orbit, and arriving at the exact time when Earth is at that location. The odds are astronomical, literally. Moreover, we'd likely see such an object coming from very far away. A Mars-sized planet, even a cold, dark one, would be detectable by infrared telescopes like the James Webb Space Telescope. It would emit thermal radiation from its internal heat. It would have a gravitational influence on other objects in the solar system. We'd know it was coming, probably years or even decades in advance. And even if a rogue planet entered the solar system, remember that space is mostly empty. The gravitational influence of the Sun and the giant planets would likely alter its trajectory. It might swing around the Sun and head back out without coming anywhere near the inner planets. Or it might collide with Jupiter or Saturn, which are much bigger targets and much more likely to intercept an incoming object. The rogue planet scenario is worth understanding because it represents the upper limit of danger, the theoretical worst case. But it's important not to conflate theoretical possibility with practical likelihood. Yes, it could happen. But the universe would have to align in extraordinarily improbable ways for it to occur. Having contemplated the absolute worst case, let's scale back down to scenarios that, while still unlikely, are at least within the realm of statistical possibility over human timescales. What about smaller interstellar objects that might actually pose a realistic threat? An object the size of the Tunguska impactor, about 50 to 60 meters across, would be large enough to cause significant damage if it struck a populated area, but small enough that it might not be detected until it was very close. Such an object, if it were made of ice or loose rocky material, might break apart in the atmosphere, creating an airburst similar to what happened over Siberia in 1908. If an interstellar Tunguska-scale object exploded over a major city, the death toll could be in the hundreds of thousands or even millions, depending on the city's population density. The blast wave would flatten buildings, start fires, and cause massive casualties. It would be one of the worst disasters in human history. But again, let's look at the probabilities. Earth's surface area is about 510 million square kilometres. The area occupied by major cities is a tiny fraction of that, perhaps a few 100,000 square kilometres if we're generous, and includes sprawling metropolitan areas. The odds of a random impact hitting a major city are less than 1 in 1,000. Most likely such an object would explode over ocean or unpopulated land. The Chelyabinsk meteor, which was about 20 meters across, represents an even smaller but more frequent class of impactor. Objects this size might hit Earth from interstellar space once every few decades or centuries, though most would be from our own solar system. The damage is localized, measured in broken windows and minor injuries rather than mass casualties. One interesting scenario that scientists have considered is an ocean impact. If an interstellar object, let's say 200 to 300 meters across, struck one of Earth's oceans, it would create a crater on the ocean floor and generate massive tsunamis. The tsunamis could inundate coastal areas for hundreds or even thousands of kilometres from the impact point. However, even this scenario has built-in mitigation. Ocean impacts don't throw as much debris into the atmosphere as land impacts do, so the climate effects would be less severe. And tsunamis, while devastating, are a regional rather than global threat. Coastal areas on the opposite side of the world might experience only minor effects. The more we think about these scenarios, the more we realise that Earth has several layers of protection. The first is statistical. Space is big, Earth is small, and the odds of a direct hit are always low. The second is atmospheric. Smaller objects burn up before reaching the ground. The third is geographical. Most of Earth is ocean or unpopulated land. And the fourth is technological. We're getting better at detecting threats, and might eventually develop the capability to deflect them. None of this is to say that the danger is zero. It's not. Over long enough timescales, Earth will eventually be hit by large objects, both from our solar system and possibly from interstellar space. But the timescales involved are measured in millions or billions of years, not decades or centuries. For any individual human, for any generation, the risk of experiencing a catastrophic impact is vanishingly small. You're far more likely to die in a car accident, from disease, or from any number of other causes than from an interstellar impact. This is the rational perspective, the one grounded in statistics and probability. And yet, there's something profound about knowing that we live in a dynamic universe, one where catastrophes are possible even if they're improbable. It reminds us of our place in the cosmos, of the fragility of our world, and of the importance of the efforts we make to understand and prepare for threats, however unlikely they may be. The first line of defence against any impact, whether from an interstellar object or a solar system asteroid, is detection. You can't deflect or prepare for a threat you don't see coming. So let's explore the current state of our ability to detect incoming objects and what improvements are on the horizon. The Pan-STARRS telescope in Hawaii, which discovered both Oumuamua and Borisov, consists of two telescopes with mirrors 1.8 meters across. It scans the sky every night, taking multiple images of the same regions over time. By comparing these images, astronomers can detect objects that have moved, distinguishing them from the stationary background of stars. This technique, called astrometry, has been used to discover thousands of asteroids, but it has limitations. The telescopes can only see objects that are bright enough to detect, which depends on the object's size, distance, and reflectivity. A small dark object at the distance of Jupiter's orbit might be invisible. A larger, brighter object at the same distance would be easy to spot. The Catalina Sky Survey in Arizona uses similar techniques with slightly larger telescopes. Together with Pan-STARRS and several other sky surveys around the world, these systems discover hundreds of near-Earth asteroids every year. They've catalogued more than 90% of the largest near-Earth asteroids, those bigger than 1 kilometre across, and they're working their way down to smaller objects. But interstellar objects present unique challenges. They're not in predictable orbits, so surveys can't focus on specific regions of sky where they're likely to appear. They're moving fast, which means they might only be visible for a short time. And if they're approaching from certain directions, like from the direction of the Sun, they might be nearly impossible to detect with ground-based telescopes. This is where space-based telescopes become important. NASA's NEOWISE mission, a space telescope that operated in infrared wavelengths, discovered hundreds of asteroids by detecting their thermal emission rather than reflected sunlight. Infrared detection is particularly useful for dark objects that reflect little visible light but still emit heat. The James Webb Space Telescope, while primarily designed for deep space astronomy, has the capability to detect objects in the outer solar system and beyond. Its infrared sensitivity could potentially spot a rogue planet or large interstellar object while it's still far from Earth. The real game changer, as mentioned earlier, will be the Vera C. Rubin Observatory. With its 8.4-metre mirror and enormous camera, it will be able to image the entire visible sky every few nights, detecting objects much fainter than current surveys can see. It's expected to increase the rate of asteroid and interstellar object discoveries by an order of magnitude. But detection is only the first step. Once an object is detected, it needs to be tracked precisely enough to determine its orbit. This requires multiple observations over time, preferably from different locations to get accurate parallax measurements. For a fast-moving interstellar object, this might mean coordinating observations from telescopes around the world. The International Astronomical Union's Minor Planet Center serves as the clearinghouse for all observations of asteroids, comets, and other small solar system objects. When astronomers discover a new object, they report their observations to the Minor Planet Center, which collects data from multiple sources and calculates the object's orbit. For an Earth-threatening object, this process would be accelerated. NASA's Planetary Defense Coordination Office would coordinate observations and analysis, working with international partners to track the object and assess the threat. They'd calculate the probability of impact, the expected impact location if a collision were inevitable, and the timeline for when it would occur. All of this depends on having enough lead time. With weeks or months of warning, precise tracking is possible. With only days, there might not be time to gather enough observations to pin down the orbit with certainty. This uncertainty could make decision-making difficult. Do you evacuate a city based on a 50% probability of impact? What if the evacuation itself causes more harm than the potential impact? These are not easy questions, and they highlight why early detection is so critical. The more time we have, the more precise our predictions can be, and the more options we have for response. Let's imagine that we've detected an interstellar object on a collision course with Earth, and we have enough warning time to attempt a deflection. What would that actually involve? How do you change the path of a massive object moving at tens of kilometers per second? The physics of deflection comes down to momentum. Momentum is mass times velocity, and to change an object's trajectory you need to change its momentum. You can do this by changing its mass, which is difficult, or by changing its velocity, which is slightly less difficult but still enormously challenging. The amount of deflection needed depends on how much time you have. If you deflect an object years before it would hit Earth, you only need to change its velocity by a tiny amount, perhaps a few centimeters per second. Over months or years, that small change accumulates, causing the object to miss Earth by a comfortable margin. But if you only have weeks or months, you need a much larger velocity change, perhaps meters per second or more. And the faster the object is moving to begin with, the more energy is required to change its velocity by a given amount. Let's consider the techniques that have been proposed or tested for asteroid deflection. The simplest conceptually is a kinetic impactor. You crash a spacecraft into the asteroid at high speed, transferring momentum and slightly changing the asteroid's velocity. NASA successfully tested this technique in September 2022 with the DART mission, which crashed a spacecraft into the small asteroid Dimorphos and measurably changed its orbit. For a solar system asteroid, this technique works well if you have enough warning time, but for an interstellar object moving at 80 kilometers per second, the mathematics become much more challenging. The relative velocity between the spacecraft and the target would be enormous, which means the impact would be more energetic, but also that the window for a successful intercept would be very narrow. Another proposed technique is a gravity tractor. This involves parking a spacecraft near the asteroid and using the spacecraft's gravitational pull to slowly tug the asteroid off course. It sounds like science fiction, but the physics is sound. Every object with mass has gravity, and if you station a massive spacecraft close enough to an asteroid for long enough, the gravitational attraction between them will change the asteroid's orbit. The advantage of a gravity tractor is precision. You can control exactly how much deflection you apply and in which direction. The disadvantage is time. Gravitational forces are weak. and it would take months or years of continuous operation to achieve a meaningful deflection. For an interstellar object that we might only detect weeks before impact, there simply wouldn't be enough time. More energetic options include nuclear deflection. A nuclear explosive detonated near an asteroid could vaporize part of its surface, creating a jet of material that acts like a rocket engine, pushing the asteroid off course. This has been studied extensively and appears technically feasible, though it raises obvious concerns about deploying nuclear weapons in space. For an interstellar object, nuclear deflection might be the only option if detection comes late. A sufficiently large nuclear device detonated at the right location could potentially deliver enough energy to change the object's trajectory by the required amount. But the engineering challenges would be immense. Launching a nuclear-armed spacecraft on short notice, intercepting an object moving at interstellar velocities, and detonating at precisely the right moment and location. There's also the question of composition. If the object is a solid rock, deflection techniques work one way. If it's a loosely bound pile of rubble held together mainly by its own weak gravity, techniques that work on solid objects might cause the asteroid to break apart rather than deflecting it. And if it's an icy comet, heating from a nuclear blast might cause unpredictable outgassing that could either help or hinder deflection efforts. The truth is, we've never deflected an interstellar object, and our only test of deflection techniques was the DART mission, which involved a small solar system asteroid under ideal conditions. Deflecting an interstellar object would be orders of magnitude more difficult, and would likely require techniques we haven't fully developed yet. In September 2022, humanity achieved something remarkable and precedent-setting. We deliberately changed the motion of a celestial body. The Double Asteroid Redirection Test, or DART, was NASA's proof-of-concept mission for planetary defense, and its success offers both hope and humbling lessons as we think about defending Earth from potential threats. The target was Dimorphos, a small moon about 160 meters across orbiting a larger asteroid named Didymos. Neither asteroid posed any threat to Earth. They were chosen specifically because they were safe, and because Dimorphos's orbit around Didymos could be measured precisely from Earth, allowing scientists to determine exactly how much the impact changed its motion. The DART spacecraft, about the size of a vending machine and weighing 610 kilograms, crashed into Dimorphos at a relative velocity of 6.6 kilometers per second. The impact was captured by a small companion satellite called Lysiacube, which had separated from DART shortly before impact and watched the collision from a safe distance. The result exceeded expectations. Dimorphos's orbital period around Didymos changed by about 33 minutes, much more than the minimum mission success threshold of 73 seconds. The impact had transferred momentum so effectively because it created a large debris cloud that acted as additional propulsion, pushing the asteroid in the opposite direction of the impact. This was good news for planetary defense. It showed that kinetic impactors work and can be quite efficient. But it also revealed complexities that would matter for real-world scenarios. The amount of deflection achieved depends heavily on the asteroid's composition and structure. Dimorphos turned out to be a rubble pile, a loosely bound collection of rocks held together by weak gravity. This is actually common for small asteroids, but it means that predicting deflection outcomes requires understanding the target's internal structure. For an interstellar object, this presents challenges. We wouldn't know its composition or structure until we got close-up observations, and by then, there might not be time to adjust our deflection strategy. The object could be solid rock, fluffy ice, a rubble pile, or some combination. Each would respond differently to impact or other deflection techniques. The DART mission also demonstrated the importance of international cooperation and rapid response capabilities. The mission was planned and executed over several years, with contributions from multiple space agencies and research institutions. For a real planetary defense scenario, especially one involving an interstellar object with limited warning time, we'd need to compress that timeline dramatically. Could we launch a deflection mission in weeks or months instead of years? Current spacecraft take months to reach even relatively nearby asteroids, and they require precise planning and numerous course corrections along the way. Intercepting an interstellar object moving at high speed would be like trying to hit a speeding bullet with another bullet, while both are fired from moving platforms. One possibility that planetary defense experts discuss is having deflection spacecraft pre-built and ready to launch on short notice. These would be kept in storage, fully fueled and tested, waiting for a potential threat to appear. When a threatening object is detected, the spacecraft could be launched quickly, cutting months off the response time. But this raises questions of cost and preparedness. Maintaining a fleet of ready-to-launch deflection spacecraft would be expensive, and the political will to fund such preparations for an extremely low-probability event is uncertain. Most likely we'd need an actual close call, an object that passes near Earth but doesn't hit, to galvanise the necessary investment. The DART mission also highlighted the importance of follow-up observations. ESA's Hera spacecraft, scheduled to arrive at Dimorphos in 2026, will conduct a detailed survey of the impact crater and measure changes in the asteroid's shape and spin. This data will refine our models and improve our ability to predict deflection outcomes for future scenarios. For interstellar objects, follow-up observations might not be possible if the deflection happens close to the impact date. We'd deflect the object, watch it pass by Earth instead of hitting, and then it would disappear back into interstellar space, leaving us uncertain about exactly what we'd accomplished and how replicable it might be for other objects. Let's consider a scenario where deflection isn't possible or doesn't work. An interstellar object is coming, we know where it will hit, and we have days or weeks to prepare. What would civil defense response look like? The first challenge is prediction accuracy. Even with good tracking data, there's always uncertainty in where an object will strike. The Earth is rotating, the object is moving, and small uncertainties in the object's orbit translate to large uncertainties in the impact location. With weeks of warning, we might be able to narrow the predicted impact zone to a band around the Earth hundreds of kilometres wide. With only days of warning, the uncertainty could span thousands of kilometres. This uncertainty complicates evacuation decisions. Do you evacuate everyone within the possible impact zone? That could mean millions or tens of millions of people. Where do they go? How do you house and feed them? What about critical infrastructure, hospitals, power plants? And what if the object ends up missing Earth entirely, or striking in a different location than predicted? The 2013 Chelyabinsk meteor caught everyone by surprise, not because it wasn't detectable, but because no one saw it coming. It approached from the direction of the Sun, making it nearly impossible to spot with ground-based telescopes. About 1,500 people were injured, mostly from flying glass when windows shattered from the shockwave. If authorities had known it was coming, they could have warned people to stay away from windows, potentially preventing most of those injuries for a larger object. The kind that would create a Tunguska-scale explosion or worse. Evacuation becomes the only option for saving lives in the immediate impact area. But evacuating a major city is enormously difficult. Hurricane evacuations from coastal cities like Houston or Miami have shown how challenging it can be to move millions of people on short notice. Roads become congested, resources run short, and some people refuse to leave. An impact evacuation would face additional challenges. With a hurricane, you evacuate away from the coast. With an impact, which direction do you go? If the impact site is uncertain, you might not know the safest direction until it's too late. And unlike a hurricane, which develops over days and follows somewhat predictable paths, an interstellar impact would come with little warning and high uncertainty until the last moments. The psychological impact of such an event would be immense. Imagine waking up to news that an object from another star system is going to hit Earth somewhere in your region within the next week. Even if the odds of it hitting your specific city are low, the fear and uncertainty would be overwhelming. People would make irrational decisions, hoard supplies, try to flee even if authorities recommended staying put. Social media would amplify both helpful information and dangerous misinformation. conspiracy theories would spread. Some would claim the government was hiding the true severity of the threat. Others would insist it was all a hoax. Managing public information and maintaining order would be nearly as important as the physical evacuation. For ocean impacts, the challenge shifts to tsunami warning and coastal evacuation. Tsunamis from asteroid impacts can travel thousands of kilometres, affecting coastlines far from the impact site, but they also take time to propagate. An impact in the Pacific Ocean might give coastal areas hours of warning before the tsunami waves arrive, time that could be used to move people to higher ground. Existing tsunami warning systems, built primarily for earthquake-generated tsunamis, could be adapted for impact scenarios. Seismic stations would detect the impact immediately. Ocean buoys would measure the tsunami waves as they passed. Computer models would predict which coastlines would be affected and how severely. Alerts would go out via emergency broadcast systems, phones, sirens. But impact-generated tsunamis can be different from earthquake-generated ones. They can be larger, faster, and more powerful depending on the impact energy and location. The models used for earthquake tsunamis might not accurately predict impact tsunamis. This uncertainty would make warnings less reliable, and evacuation decisions more difficult. For atmospheric airbursts like Tunguska or Chelyabinsk, the warning might be so short that evacuation is impossible. The object enters the atmosphere and explodes within seconds or minutes. The only preparation would be public awareness campaigns teaching people what to do if they see a bright fireball. Take cover, stay away from windows, protect your head. The more we think about civil defence for impacts, the more we realise that prevention through deflection is vastly preferable. Evacuation is a last resort fraught with difficulties and uncertainties. This is why investment in detection and deflection capabilities is so important, even for very low probability events. An impact threat, especially from an interstellar object that could strike anywhere on Earth with little warning, is inherently a global problem requiring global coordination. But coordinating an effective response across nearly 200 countries with different languages, political systems and levels of technological development is extraordinarily challenging. The United Nations has recognised this through the establishment of the International Asteroid Warning Network and the Space Mission Planning Advisory Group. These organisations bring together space agencies, astronomical observatories, and civil defence organisations from around the world to share information about potential impact threats and coordinate response planning. But these are relatively new institutions, established only in the past decade or so, and they've never been tested by a real threat. Their protocols and communication channels work fine for sharing information about newly discovered asteroids under non-emergency conditions. Whether they could coordinate an effective response to an imminent impact with days or weeks of warning is an open question. Consider the political complexities. If a deflection mission is needed quickly, which nation or space agency takes the lead? Who pays for it? What if the deflection attempt fails and changes the impact location from one country to another? Is that an act of war? What if a nuclear deflection is proposed but some nations object to deploying nuclear weapons in space? These aren't just hypothetical questions. They're the kind of issues that would need to be resolved in real time under enormous pressure if a genuine threat appeared. Having clear agreements and protocols in place beforehand is essential, but achieving international consensus on these matters during peacetime for an extremely low probability event has proven difficult. The European Space Agency, NASA, JAXA, Japan, Roscosmos, Russia, and other space agencies have signed agreements to share data about near-Earth objects and to coordinate observations. But these agreements don't extend to decision-making authority for deflection missions or civil defence responses. One model that has been proposed is to designate a lead space agency based on who detected the object first or who has the best capability to respond. That agency would coordinate with others, but would have the authority to make time-critical decisions. This is similar to how international maritime law designates which nation is responsible for coordinating rescue operations, based on whose waters or rescue coordination zone an incident occurs in. But space is not territorial waters. An object approaching Earth from interstellar space doesn't belong to anyone and threatens everyone. The lack of clear jurisdiction could lead to paralysis or conflict at exactly the moment when unified action is most needed. There's also the question of developing nations. Many countries lack space programs or advanced astronomical capabilities. They depend on others for detection and tracking of threats. If an impact were predicted to strike a developing nation, would wealthier nations provide aid for evacuation and civil defence? Would they share all available information, or would national security concerns limit data sharing? The COVID-19 pandemic showed both the potential for global coordination and its limitations. When the virus emerged, the world came together in some ways, sharing genetic sequences and research data. But it also fractured in others, with vaccine nationalism and failure to help poorer nations. An impact threat would likely show similar patterns: cooperation in some areas, competition or neglect in others. Cultural and linguistic barriers add another layer of complexity. Emergency communications need to reach everyone, but translating accurate information into hundreds of languages while maintaining clarity and avoiding panic is extremely difficult. Misinformation spreads faster than official information, especially during crises. Some have proposed that the threat of an asteroid or interstellar impact could unite humanity in unprecedented ways. The common enemy might overcome political divisions and lead to genuine global cooperation. This is a hopeful vision, and there's some evidence from past crises that external threats can bring people together. But it's equally possible that an impact threat would exacerbate existing tensions. Nations might hoard resources, conspiracy theories might flourish, blame might be assigned to those who failed to detect the threat earlier or to deflect it successfully. The aftermath of an impact, especially one that caused significant casualties, could be politically destabilizing. The rational approach is to prepare now, during calm times, when decisions can be made thoughtfully rather than under pressure. This means establishing clear protocols, conducting international exercises and simulations, and building the relationships and trust that would be needed during a real crisis. Some of this is happening through the UN organisations and bilateral agreements between space agencies, but much more could be done. What's needed is something like the international frameworks for nuclear weapons, pandemic response, or climate change. Treaties and institutions that have real authority and resources, not just advisory roles. Whether the political will exists to create such frameworks for a very low probability threat remains to be seen. To truly understand the threat from interstellar objects, it helps to step back and look at Earth's long history of impacts. Our planet bears the scars of countless collisions over its 4.5 billion year existence, though most of those scars have been erased by weathering tectonics and life's relentless activity. What remains tells a story of a dynamic solar system and a planet that has been both destroyed and renewed by impacts. The earliest period of Earth's history, called the Hadean Eon, was violent beyond imagination. This was a time from 4.6 to 4 billion years ago, when the solar system was still full of debris from its formation. Countless objects, from dust grains to planet-sized bodies, crashed into each other in a chaotic dance of creation and destruction. Earth itself is thought to have formed through countless impacts, small bodies colliding and sticking together through gravity, gradually building up from a cloud of dust and gas to a molten ball of rock. The most dramatic impact occurred about 4.5 billion years ago, when a Mars-sized object called Theia struck the young Earth. The impact was so energetic that it melted both bodies, and debris from the collision coalesced to form our moon. Think about that for a moment. Our moon, that serene companion that lights our nights and pulls our tides, is the result of the most catastrophic impact in Earth's history. The collision that created it likely vaporized Earth's crust and created a magma ocean hundreds of kilometers deep. Nothing could have survived such an event, but of course, there was nothing alive to survive it yet. Following the giant impact, Earth went through a period called the Late Heavy Bombardment, roughly 4.1 to 3.8 billion years ago. During this time, the inner solar system experienced a surge in impacts, possibly caused by the migration of the giant planets, destabilizing the asteroid belt and sending debris flying inward. Craters from this period still scar the Moon's surface, and Earth would have been hit even more heavily due to its stronger gravity, though evidence has been lost to geological processes. Amazingly, life appeared on Earth very soon after the Late Heavy Bombardment ended, perhaps as early as 3.8 billion years ago. This suggests that impacts, while destructive, might have also delivered the organic compounds and water necessary for life to begin. Some scientists even propose that life itself might have been brought to Earth by impacting comets or asteroids, an idea called panspermia. Since the end of the heavy bombardment, impacts have become less frequent but still occasional enough to shape Earth's history. About 2 billion years ago, a large object struck what is now South Africa, creating the Vredefort crater, now about 300 kilometres across, though originally much larger. This is the largest verified impact structure on Earth, representing a collision with an object perhaps 10 to 15 kilometres across. More recently, geologically speaking, was the Chicxulub impact 66 million years ago that we discussed earlier. This wasn't the only major impact of the past 100 million years, just the most famous because of its association with the dinosaur extinction. The Chesapeake Bay impact, about 35 million years ago, created a crater 85 kilometres wide. If that happened today, it would devastate the eastern United States. What's striking when you look at Earth's impact history is not just the violence, but the resilience. After every major impact, even the most catastrophic ones, life eventually recovered and often diversified. The Chicxulub impact ended the age of dinosaurs but opened ecological niches that allowed mammals to flourish. In the long run, impacts have been agents of change as much as destruction. But here's an interesting question. In all of Earth's impact history, has an interstellar object ever struck our planet? The honest answer is, we don't know. And we probably can't know. Most impact craters have been erased by erosion and plate tectonics. Those that remain show no obvious signs of being from interstellar objects, rather than solar system ones. The chemistry and mineralogy of impact debris don't preserve information about the impactor's origin. It's entirely possible that some of Earth's ancient impacts were caused by interstellar visitors. Statistics suggest it's unlikely, but not impossible. If interstellar objects pass through the inner solar system at a rate of 1 or 2 per year, and Earth has existed for 4.5 billion years, then hundreds of millions of interstellar objects have passed by during that time. Some might have struck Earth, but distinguishing their impacts from those of solar system objects is probably impossible with current techniques. When we think about threats from space, we often focus on the asteroid belt between Mars and Jupiter, or on near-Earth asteroids that cross our planet's orbit. But there's another region of the solar system that deserves attention: the Oort cloud, a vast spherical shell of icy objects surrounding the Sun at enormous distances. The Oort cloud begins somewhere around 2,000 astronomical units from the Sun, and extends to perhaps 100,000 AU or more, nearly halfway to the nearest stars. It's thought to contain trillions of icy objects, ranging from small snowballs to bodies the size of mountains. These are the remnants of the solar system's formation, objects that were ejected outward by gravitational interactions with the giant planets, and now orbit in a vast, cold reservoir at the edge of interstellar space. Most of the time, Oort cloud objects stay where they are, following their slow, stable orbits. But occasionally, something disturbs them. A passing star, the gravitational tide of the Milky Way galaxy, or perhaps a rogue planet passing through the outer solar system, can nudge an Oort cloud object, changing its orbit and sending it falling inward toward the Sun. These objects become the long-period comets we occasionally see from Earth, visitors from the outer darkness that swing around the Sun and then retreat back to the depths. Comets like Hale-Bopp, Hyakutake, and many others have this origin. They appear without warning because their orbital periods are thousands or even millions of years. Now here's where things get interesting in the context of interstellar objects. The boundary between the Oort cloud and interstellar space is fuzzy. Objects at the outer edge of the Oort cloud are only weakly bound to the Sun. A relatively gentle gravitational nudge from a passing star could send them into interstellar space. Or conversely, an interstellar object passing through the outer solar system could be captured into an Oort cloud orbit. This raises a fascinating possibility. Some objects we think of as part of the solar system might actually be captured interstellar objects. They could have formed around other stars, been ejected into interstellar space, and then captured by the Sun's gravity as they pass through the outer solar system. They'd now be indistinguishable from native Oort cloud objects. Similarly, objects currently in the Oort cloud might eventually be ejected into interstellar space by future stellar encounters. The Sun is not alone in the galaxy. It orbits the galactic centre along with hundreds of billions of other stars. Every few 100,000 years, another star passes within a few light years of the Sun. Close enough to perturb Oort cloud objects, there have been several stellar encounters in the past that we know about. About 70,000 years ago, a red dwarf star called Schultz's star passed within about 0.8 light years of the Sun, close enough to potentially disturb the outer Oort cloud. In about 1.3 million years, the star Gliese 710 will pass even closer, within about 0.16 light years, definitely close enough to send a shower of comets toward the inner solar system. These stellar encounters are a natural part of galactic life. They don't pose a direct threat to Earth, but they do increase the likelihood of comets being perturbed into the inner solar system. Some scientists have proposed that mass extinctions on Earth might be correlated with these encounters, as increased comet activity would mean more potential impactors. The connection to interstellar objects is this. The Oort cloud serves as a kind of buffer zone between the solar system and interstellar space. It's both a source of objects that leave the solar system and a potential capture zone for interstellar visitors. An object like 2I/Borisov, if it had approached from a different angle or at a different velocity, might have been captured into a long elliptical orbit rather than passing straight through. In fact, some astronomers have speculated that Oumuamua might have been in the solar system for a long time, orbiting in the outer reaches, before something perturbed its orbit and sent it plunging through the inner solar system, where we finally detected it. This is unlikely, but not impossible. If true, it would mean interstellar objects might be hiding in the Oort cloud, waiting to be nudged inward. The Oort cloud also tells us something about how common planetary systems might be. If every star has an Oort cloud-like structure filled with trillions of icy objects, and if stellar encounters occasionally disrupt these clouds, then interstellar space should be full of these wandering objects. The galaxy, from this perspective, is not a collection of isolated planetary systems, but an interconnected web where material constantly exchanges between stars. Let's return to the central question we started with, the one that perhaps brought you to this exploration in the first place. What's the worst-case scenario for Earth from an interstellar object? And more importantly, how likely is it? We've examined the physics, the history, the detection, and defense capabilities. Now it's time to put actual numbers to the risk and understand what they mean in human terms. The probability of an interstellar impact depends on several factors that we can estimate with varying degrees of confidence. First, how often do interstellar objects pass through the inner solar system? Based on the discovery of Oumuamua and 2I/Borisov, and accounting for what we likely missed, astronomers estimate that objects larger than about 100 meters in diameter pass through the inner solar system a few times per year. Smaller objects too small to cause significant damage are probably much more common, perhaps dozens or hundreds per year. Larger objects, those that would pose an existential threat, are correspondingly rarer, perhaps once per decade or century for objects the size of a small mountain. Second, what's the probability that any given object will hit Earth? This is purely geometric. Earth's cross-sectional area compared to the area of a sphere with a radius of Earth's orbit around the Sun gives us that 1 in 22 million chance we calculated earlier. Of course, this is simplified. Gravity focuses incoming objects slightly, increasing the effective target area. But the basic probability remains very small. Multiply these together. If large interstellar objects pass through the inner solar system once per century, and each has a 1 in 22 million chance of hitting Earth, then the average time between large interstellar impacts is about 2.2 billion years. That's half the age of the Earth itself. For comparison, large solar system asteroids hit Earth more frequently because there are more of them, and some are in Earth-crossing orbits. The average time between Chicxulub-scale impacts from solar system objects is estimated at 50 to 100 million years. So interstellar impacts are roughly 20 to 40 times rarer than comparable solar system impacts. Now, let's put this in perspective. A time interval of 2.2 billion years is so long that it's almost meaningless in human terms. Recorded human history spans about 5,000 years. Anatomically modern humans have existed for about 300,000 years. All of human civilization, from the first agricultural settlements to the present day, represents less than 0.001% of that 2.2 billion year interval. The probability of a large interstellar impact occurring in any given human lifetime is astronomically small, far smaller than countless other risks we face without worry. You're more likely to be struck by lightning, to win a major lottery, to be killed by a falling coconut, than to experience an interstellar impact event. But probabilities can be counterintuitive. Just because something is extremely unlikely doesn't mean it's impossible. There's a chance, however small, that an interstellar object could strike Earth tomorrow. The laws of physics don't forbid it. They just make it very, very unlikely. This is where risk assessment becomes more art than science. How do we prepare for events that are possible but highly improbable? How much should society invest in planetary defense against interstellar threats compared to other risks that are both more likely and more controllable? Some argue that the investment should be minimal. The threat is too remote, and resources would be better spent on immediate concerns. Climate change, disease, poverty, conventional conflicts. Others argue that the potential consequences are so severe that even a tiny probability justifies substantial investment. An extinction-level event, however unlikely, would be infinitely costly, so preventing it has infinite value. The practical middle ground is to invest in capabilities that serve multiple purposes. Better telescopes that can detect interstellar objects also detect near-Earth asteroids, which pose a more immediate threat. Deflection technologies developed for asteroid defense would work against interstellar objects. Civil defense systems that could handle an impact warning would also be useful for other disasters. From this perspective, preparing for interstellar impacts isn't a separate category of concern, but part of a broader planetary defense and disaster preparedness framework. We're not building capabilities specifically for interstellar threats. We're building general capabilities that would apply to interstellar threats among many others. Beyond the mathematics and physics, beyond the practical questions of detection and deflection, there's a deeper philosophical dimension to thinking about interstellar impacts. These potential events connect us to the larger scales of space and time and raise questions about humanity's place in the cosmos. One such question is this: what does it mean to live in a universe where catastrophe is always possible but rarely occurs? We exist in a state of statistical grace, protected by nothing but the vastness of space and the laws of probability. Every day that passes without an impact is not because we've done something right, but because the dice simply haven't come up against us. This can feel uncomfortable. Humans like to feel in control of their fate. We build walls against floods, develop vaccines against diseases, create laws to prevent violence. But against cosmic threats like interstellar impacts, our control is limited. We can improve our odds slightly through detection and deflection, but ultimately we remain at the mercy of probability. Some find this unsettling. It reminds us of our fragility, of how contingent our existence is. Earth is a small world in a vast universe, and it exists in a state of temporary grace. Other civilizations, if they exist or have existed on other worlds, might not have been so lucky. Their worlds might have been struck at critical moments in their development, their potential extinguished by bad cosmic luck. But there's another way to look at it, one that's perhaps more peaceful. The very fact that Earth has survived for 4.5 billion years, that life has persisted and evolved, that we are here to contemplate these questions, is testament to the resilience of our planet and the forgiving nature of cosmic statistics. We live in a universe that is dangerous but not malevolent. Interstellar objects don't seek us out. They simply move according to the laws of physics, and those laws overwhelmingly work in our favour. The same vast distances that make us feel isolated and alone are also what protect us. We are safe because we are insignificant, and there's a certain peace in that. Consider too what interstellar objects represent. They are messengers from other worlds, physical samples of distant planetary systems delivered to our doorstep. Each one carries information about conditions elsewhere in the galaxy, about the chemistry of other star systems, about the processes of planet formation and evolution. The study of 2I/Borisov revealed that comets from other stars are similar to our own. This suggests a kind of cosmic homogeneity, a universality of the laws of chemistry and physics. Water ice forms the same way whether it's around our sun or around a star 100 light-years away. Carbon and nitrogen and oxygen combine in familiar ways. This tells us something profound. The universe is fundamentally comprehensible. The rules we learn by studying our solar system apply elsewhere. This gives us confidence that our understanding of cosmic threats is grounded in real physics, not speculation. There's also something humbling about the deep timescales involved. When we talk about average impact intervals of millions or billions of years, we're engaging with timescales that dwarf human history. This puts our concerns and conflicts in perspective. The things we worry about on a daily basis, politics, economics, social conflicts, operate on timescales of years or decades. The great historical arcs we study, the rise and fall of civilizations, the evolution of technologies, the spread of ideas, operate on timescales of centuries or millennia, but the cosmos operates on timescales of millions and billions of years. From a cosmic perspective, all of human history is a brief flicker. We've existed for an evolutionary instant, and we might be gone just as quickly, or we might endure, spread to other worlds, and outlast even our sun. The cosmic perspective doesn't tell us which future awaits, but it reminds us that our time here is precious precisely because it's temporary. Interstellar impacts also connect us to the broader galactic community of planetary systems. Every star probably has or had planets. Many of those systems probably send objects into interstellar space, just as ours does. The galaxy is full of wandering debris, material that once orbited other stars, that formed in other planetary nebulae, that might even have supported life. When we detect an object like 2I/Borisov, we're seeing a piece of another world's history. We're connected, however tenuously, to whatever story played out in that distant system. Did planets form and flourish there? Did life evolve? Or was it a sterile system, just rocks and ice orbiting a distant sun? We may never know, but the questions themselves are worth asking. They expand our sense of place and purpose. We're not isolated inhabitants of a lonely planet, but participants in a galaxy-wide exchange of matter and information that has been going on for billions of years. As we approach the end of our exploration, it's worth reflecting on what it means to live with the kind of uncertainty that interstellar impacts represent. How do we hold in our minds the knowledge that catastrophe is possible, however unlikely, without letting that knowledge paralyze us or fill us with fear? This is not just a question about cosmic threats. It's a fundamental challenge of human existence. We all live with uncertainty. We don't know when or how we'll die. Whether tomorrow will bring joy or sorrow, whether our plans will succeed or fail, life is inherently unpredictable, and yet we must make choices and live our lives as if we have some control over our fate. The key, perhaps, is to distinguish between productive concern and unproductive worry. Productive concern leads to preparation and action. It motivates us to improve detection systems, develop deflection technologies, and plan for civil defence. It drives scientific research and international cooperation. Unproductive worry, on the other hand, focuses on threats we can't control and fixates on worst-case scenarios that are extremely unlikely. It creates anxiety without leading to useful action. It makes us feel vulnerable and afraid without providing any benefit. The rational approach to interstellar impact is productive concern. We acknowledge the threat, invest reasonably in preparation, and then go about our lives. We don't ignore the danger. But we don't let it dominate our thinking either. We accept that we live in a dynamic universe where threats exist, and we do what we can to mitigate them while recognising that absolute safety is impossible. This balanced approach is how we handle many other low-probability, high-consequence risks. We buy insurance for our homes even though the chance of a major loss is small. We wear seatbelts even though most car trips don't end in accidents. We maintain fire departments even though most buildings never catch fire. Planetary defence is similar. We invest in capabilities not because we expect to use them, but because the consequences of being unprepared, should the need arise, would be catastrophic. It's insurance on a planetary scale. There's also something empowering about understanding threats clearly. When we know what we're facing, when we understand the probabilities and mechanisms, fear diminishes. Mystery and ignorance breed anxiety. Knowledge, even knowledge of dangers, brings a kind of peace. This is why education about cosmic threats is important. When people understand that interstellar impacts are possible but extremely rare, that we're actively monitoring for threats, and that we're developing capabilities to respond, they can put the danger in proper perspective. They don't need to be afraid because they understand the actual level of risk. For children especially, learning about these topics should be balanced with reassurance. Yes, objects from other star systems pass through our solar system, and yes, in principle, one could hit Earth. But it's extraordinarily unlikely, and even if it happened, there's so much empty space on our planet that the chances of it affecting any particular person are vanishingly small. The universe is vast and mostly empty, and that emptiness is our protection. We're safe not because of walls or weapons, but because of distance and probability. This is a different kind of safety than we're used to, one that requires trusting in mathematics rather than human defences. There's also a certain freedom in accepting uncertainty. If we acknowledge that we can't control everything, that the universe will do what it will regardless of our wishes, then we can focus on what we can control, our response, our preparation, our resilience. This applies to interstellar impacts and to life in general. We can't prevent every bad thing from happening, but we can choose how we prepare for and respond to challenges. We can build supportive communities, develop robust systems, and maintain the flexibility to adapt when things don't go as planned. The societies that will handle cosmic threats best, whether from interstellar objects or other sources, are not necessarily those with the most advanced technology. They're societies that can coordinate effectively, share information honestly, make decisions rationally, and support each other through crises. These are human qualities, not technological ones. In this sense, preparing for interstellar impacts is really about becoming better as a civilization. It's about developing the wisdom to assess risks accurately, the will to invest in long-term safety, the cooperation to work across national boundaries, and the resilience to recover from setbacks. These are qualities worth cultivating regardless of whether an interstellar object ever threatens Earth. They'll serve us well for all the challenges we face, both cosmic and terrestrial, and in developing them, we become a more mature species, one that can look at the universe not with fear, but with understanding and appropriate preparation. As we drift into the final portion of our exploration, it's time to step back even further and consider the truly big picture. What do interstellar objects tell us about the nature of the universe and our place within it? When Oumuamua was first detected, there was a moment of collective wonder. For the first time in human history, we had definitive proof of an object from beyond our solar system. We had always known, intellectually, that other star systems must exist and must produce debris. But knowing and seeing are different things. That small, tumbling object, already receding into the darkness by the time we spotted it, was a physical connection to the wider galaxy. It had been shaped by different processes around a different star in a different planetary system. Yet here it was, passing through our cosmic neighbourhood, close enough for us to photograph and study. This tells us something important. The galaxy is not a collection of isolated islands. Stellar systems are not hermetically sealed. They leak material into interstellar space constantly. Planets eject comets. Asteroid collisions create fragments that escape. Massive planets slingshot smaller objects outward at escape velocity, over billions of years. This process has filled the galaxy with wandering debris. Current estimates suggest there might be more interstellar objects than there are stars in the Milky Way. Trillions upon trillions of rocks, ice balls, and who knows what else, drifting through the darkness between stars. Some of these objects might carry organic compounds or even simple life forms in a dormant state. If this is true, then life might spread through the galaxy, not through intentional missions, but through natural processes. Hitchhiking on rocks that happen to land on suitable worlds. This is speculative, but not impossible. It means that Earth's life might not be entirely native. Some of the organic compounds that became the building blocks of Earth's biochemistry might have arrived via impacting comets, either from our solar system or from interstellar space. We might be, in a very literal sense, made of star stuff that has travelled between the stars. This interconnectedness extends beyond just material exchange. The entire galaxy is a dynamic system where stars influence each other. The stellar encounter we mentioned earlier. Schultz's star passing within 0.8 light-years 70,000 years ago probably disturbed the Oort cloud. Material was sent inward and outward. Some objects that were part of our solar system became interstellar. Some interstellar objects might have been captured. Over the 4.5 billion years of our solar system's existence, hundreds or thousands of stars have passed nearby. Each encounter shuffles the deck, exchanging material between systems. The sun itself is moving through the galaxy, passing through different regions with different densities of stars and interstellar material. Currently, we're in what's called the local bubble, a region of space about 300 light-years across where the interstellar medium is hot and thin, heated by ancient supernova explosions. In a few million years, our solar system will drift into a different region with different conditions. These changes affect the environment around us, the rate of cosmic ray bombardment, the density of interstellar gas and dust. All of this happens on timescales too slow for humans to perceive directly, but it shapes the context in which life on Earth exists. We're not living in a static, unchanging universe. We're travelling through a dynamic galaxy, and conditions around us are slowly shifting. The study of interstellar objects gives us a window into this larger galactic context. Each object is a data point telling us about conditions elsewhere. By studying many such objects over time, we'll build up a picture of what the galaxy is like beyond our immediate neighbourhood. We'll learn about the chemistry of different stellar environments. We'll see what kinds of planetary systems are common and what are rare. We might even detect objects that are obviously artificial, though this is highly speculative. But the point is, interstellar objects are not just potential threats, they're opportunities for learning. This is why the scientific community was so excited about Oumuamua and Borisov. Yes, they represented a new category of potential hazard that needed to be assessed, but more importantly, they represented a new way to study the galaxy. We don't have to travel to other star systems to learn about them. Sometimes, They send samples our way. The future of this field is promising. As detection systems improve, we'll discover more interstellar objects. Some will be comets like 2I/Borisov. Some will be asteroids. Perhaps we'll find truly exotic objects, chunks of solid hydrogen, fragments from neutron star collisions, or even the hypothetical alien probe that Oumuamua was briefly speculated to be. Each discovery will expand our understanding, and each will remind us that we're part of something much larger than ourselves, participants in a galaxy-wide exchange of matter and information that has been ongoing for billions of years and will continue long after humanity is gone. One of the most remarkable aspects of Earth's history is not that it has been struck by asteroids and comets, it certainly has, but that life has persisted through these impacts and emerged stronger and more diverse afterward. This resilience tells us something important about both the nature of life and the nature of cosmic threats. Life on Earth has survived every mass extinction in the geological record. After the Chicxulub impact 66 million years ago, which killed the non-avian dinosaurs and about 75% of all species, life recovered. It took time. Ecosystems don't bounce back overnight. But within a few million years, new species had evolved to fill the vacant ecological niches. The survivors of that impact weren't necessarily the strongest or most advanced. They were the most adaptable, the ones who could survive in harsh conditions, who didn't depend on ecosystems that had collapsed. Small mammals, burrowing animals, scavengers, seeds and spores that could lie dormant. These were the inheritors of the post-impact world. This pattern has repeated after every major extinction event. Life finds a way, not because it's trying to survive, but because any organism that can survive in changed conditions will reproduce, and over time, new species will evolve from these survivors. An interstellar impact, even a large one, would likely follow this pattern. Unless the impact was truly catastrophic, planet-shattering, atmosphere-stripping, some life would survive. Deep-sea organisms far from the impact site, microbes living in rocks kilometres underground, spores and seeds scattered across the globe, extremophils adapted to harsh conditions. These survivors would be the seed from which life would recover. Given millions of years, new ecosystems would evolve. The world might look very different. New species, new ecological relationships, new dominant forms of life. But it would be alive. This is both comforting and humbling. Comforting because it suggests that even the worst cosmic disasters probably won't sterilize Earth completely. Life is too diverse, too adaptable, too widespread. Humbling because it reminds us that humanity's survival is not guaranteed. We're adaptable and intelligent, but we're also dependent on complex systems that might not survive a major impact. If a large interstellar object struck Earth, humanity might not survive even if life in general did. Our population is concentrated in cities. Our food systems are globalized and fragile. Our societies depend on electricity, communication, transportation. An impact that disrupted these systems could cause cascading failures that might be harder to survive than the impact itself. But it's also worth considering that humanity has capabilities no other species has ever possessed. We can detect threats before they arrive. We can potentially deflect them. We can store knowledge and technology in ways that might survive disasters. We can cooperate across vast distances and coordinate responses to global threats. These capabilities are new in Earth's history. Life has existed for 3.8 billion years, but only in the last few decades have we developed planetary defense capabilities. Only in the last century have we developed the scientific understanding necessary to even comprehend cosmic threats. This is both a tremendous achievement and a tremendous responsibility. We are, as far as we know, the only species on Earth with the capability to protect not just ourselves, but all of Earth's life from cosmic impacts. If we develop robust deflection capabilities, we could prevent impacts that would otherwise cause mass extinctions. We could be, in a sense, the guardians of Earth's biosphere. This is a strange and profound role. Evolution didn't design us for this purpose. We're here by accident, the result of countless random mutations and environmental changes. Yet here we are, capable of looking up at the sky, understanding the threats that lurk there, and potentially doing something about them. Whether we rise to this challenge or not will say a lot about us as a species. It will show whether we can think beyond immediate concerns, invest in long-term safety, and cooperate effectively on a global scale. These are not easy things, and there's no guarantee we'll succeed. But the resilience of life suggests that even if we fail, even if humanity doesn't survive some future catastrophe, life itself will continue. Other species will evolve, perhaps some that are even more capable than we are. The experiment of life on Earth won't end with us, though our chapter in it is still being written. There's a certain peace in this perspective. It removes some of the pressure. We don't have to save everything. We can't. What we can do is try our best, use our capabilities wisely, and hope that it's enough. And if it's not, well, life will continue in some form, and perhaps something wonderful will evolve in our wake. As we consider what interstellar objects mean for Earth, it's worth thinking about what they might mean for other worlds. We now know, thanks to missions like Kepler and TESS, that planets are common around other stars. Most stars have planetary systems, and many of those systems include rocky, Earth-sized planets. Some of these planets orbit in their star's habitable zone, the region where temperatures allow liquid water to exist on the surface. These are the worlds most likely to harbour life, at least life as we understand it. Estimates suggest there could be billions of potentially habitable planets in the Milky Way galaxy alone. Each of these worlds faces the same cosmic risks that Earth does. They're in solar systems filled with asteroids and comets. They're in a galaxy where interstellar objects drift between the stars. Some of these worlds might be luckier than Earth, experiencing fewer impacts. Some might be less lucky, suffering frequent catastrophic collisions. The impact history of a planet can profoundly affect whether life evolves there and what forms it takes. Too many impacts, and life might never get established or might be repeatedly sterilized. Too few, and the planet might not receive the organic compounds and water delivered by impacting bodies. There might be a quotate for impact rates, just right to foster the development of complex life. Earth might be in this zone. We've had enough impacts to deliver necessary materials and create evolutionary opportunities through mass extinctions, but not so many that life couldn't persist and evolve. This might not be coincidence. It might be selection bias. We're here to ask these questions precisely because Earth's impact history allowed us to evolve. When we detect an interstellar object like 2I/Borisov, we're seeing evidence of the same processes at work in other planetary systems. That comet came from somewhere, ejected by gravitational interactions in some distant system. That system presumably still exists, still has planets, still sends objects into interstellar space. If we could study enough interstellar objects, we could learn about the characteristics of many planetary systems without ever visiting them. We could determine what percentage have ice-rich comets, what percentage have rocky asteroids, what percentage might have unusual compositions suggesting exotic conditions. This is important for the search for extraterrestrial life. If we know what kinds of planetary systems are common, we can better target our search for habitable worlds. We can also understand what conditions might prevent life from developing, helping us interpret the silence we've encountered in our search for intelligent signals from other civilizations. One sobering possibility is that many potentially habitable worlds are struck by large impactors at critical moments in their development. Perhaps life arises frequently, but is often snuffed out before it can become complex or intelligent. The universe might be full of worlds that had the potential for life, but never fulfilled it due to bad cosmic luck. Alternatively, impacts might be essential for life. The Chicxulub impact killed the dinosaurs but allowed mammals to flourish. Without it, intelligent life on Earth might not have evolved, at least not in the form it did. Perhaps impacts are not just dangers but opportunities, creating the disruptions that drive evolution forward. We can't know which of these scenarios is correct without more data. We need to study many planetary systems, many interstellar objects, and ideally discover life on other worlds to see how common it is. But the questions themselves are fascinating and connect our understanding of cosmic threats to the broader question of life in the universe. There's also the possibility, however remote, that we'll detect an obviously artificial interstellar object, a space probe from another civilization, perhaps launched millions of years ago, drifting through the galaxy. This is what some speculated Oumuamua might be, though the evidence didn't support that hypothesis. If we did detect such an object, it would be the most profound discovery in human history. It would prove we're not alone, that other intelligences exist or existed. It would also raise immediate questions. Where did it come from? Why was it sent? Is it a threat or an opportunity? These are fun to speculate about, but they remain speculation. So far, every interstellar object we've detected has had natural explanations. The universe is strange enough without invoking alien technology. But we should remain open to the possibility, and future discoveries might surprise us. As our exploration draws toward its close, let's consider an ethical dimension. What do we owe to future generations when it comes to planetary defense and the threat of interstellar impacts? This is not an abstract question. The decisions we make today about investing in detection systems, developing deflection technologies, and establishing international coordination frameworks will affect humanity's ability to respond to threats decades or centuries from now. Some argue that we have a moral obligation to future generations to leave them a safer world. We didn't choose to be born into a universe with cosmic hazards, and neither will they. The least we can do is develop and maintain the capabilities to detect and deflect threats, giving our descendants a fighting chance if one appears. This argument has force, but it's complicated by the fact that planetary defense competes with other priorities. Money spent on asteroid detection isn't spent on education, healthcare, or addressing climate change. How do we balance low probability, high consequence threats against immediate certain problems? One framework for thinking about this is to ask, what would we want previous generations to have done for us? If our ancestors in the 19th or early 20th century could have invested in capabilities that would protect us today, would we want them to have done so? The honest answer is probably yes. But only to a reasonable extent. We'd want them to have laid groundwork, established institutions, developed basic technologies. But we wouldn't expect them to have solved all our problems or to have sacrificed their well-being for ours. Each generation has to live its own life while also preparing for the future. Applied to planetary defense, this suggests a middle path. We should invest enough to maintain awareness of potential threats, to develop basic deflection capabilities, and to establish frameworks for international cooperation. But we shouldn't bankrupt ourselves or neglect immediate concerns in pursuit of perfect safety from cosmic threats. We also owe future generations knowledge. The research being done today on asteroids, comets, and interstellar objects builds a foundation of understanding that will be valuable for centuries. Every discovery, every mission, every analysis contributes to a body of knowledge that can't be easily lost. This is why scientific research is so important, even research that doesn't have immediate practical applications. When we study Borisov, we're not just satisfying curiosity, we're building knowledge that might prove crucial if another, more threatening interstellar object appears in the future. There's also an argument that we owe it to future generations not to succumb to fear or paralysis. The universe contains threats, but it also contains wonders. We should face those threats rationally and calmly, modelling for those who come after us how to live with uncertainty without being consumed by it. If we respond to cosmic threats with panic, with excessive spending on unlikely scenarios, or with fatalism and resignation, we're teaching future generations unhelpful lessons. If instead we respond with careful assessment, proportional investment, and continued focus on the things we can control, we're modelling wisdom. Perhaps the greatest gift we can give future generations is a civilization that's resilient, cooperative, and scientifically literate. These qualities will serve them well for whatever challenges they face, cosmic or otherwise. A civilization that can work together across national boundaries, that values scientific truth, that can assess risks rationally and respond proportionally, such a civilization can handle cosmic threats. But more than that, it can handle all the other challenges that will inevitably arise. New diseases, climate shifts, resource scarcity, social conflicts. Planetary defense from this perspective is not just about preventing impacts. It's about building the kind of civilization that can face any challenge and has the wisdom, cooperation, and resilience to overcome it. In these final moments of our exploration, let's reflect on what thinking about interstellar impacts gives us, beyond just an understanding of the threat itself. There's a gift in contemplating cosmic dangers, a shift in perspective that can be surprisingly peaceful. When you think about the vast timescales involved, billions of years between major impacts, your own concerns and worries naturally shrink. The things that seemed urgent and important an hour ago might feel less pressing when viewed against the backdrop of cosmic time. This isn't to say that your concerns don't matter, they do. But there's a kind of peace that comes from realizing that the universe operates on scales that dwarf human experience. Your problems are real, but they're also temporary. The universe was here long before you and will continue long after you're gone, and there's something oddly comforting in that continuity. Thinking about interstellar objects also connects us to the rest of the galaxy in a tangible way. When you look up at the night sky and see stars, you're seeing the sources of these wandering objects. Some of those stars might have ejected comets or asteroids that are now drifting through interstellar space, perhaps heading our way, perhaps not. Every star might have sent ambassadors into the void, whether intentionally or through natural processes. These objects carry information about their home systems, information we can learn if we're patient and careful. They're a kind of message, though not in the conventional sense. They say, we're here, we're diverse, we're dynamic. The study of these objects reminds us that we're not isolated. Earth is part of a galactic ecosystem, connected to other star systems through the slow exchange of material and information. This should make us feel less alone. Even though the distances involved are so vast that direct communication or contact seems impossible with current technology, there's also something humbling in realizing how much we don't know. We've detected exactly 2 interstellar objects with certainty. 2, out of potentially billions or trillions passing through the galaxy at any given time. Our sample size is laughably small, yet from it we're trying to understand general principles. This should make us cautious about our conclusions. Yes, interstellar objects seem to be similar to solar system objects, at least the ones we've seen. But there could be entire categories of objects we haven't encountered yet. Strange ice compositions, exotic minerals, structures we can't even imagine. The universe is always more diverse and stranger than we expect. Every time we think we understand something, nature reveals new complexity. This pattern has repeated throughout the history of science, and there's no reason to think it will stop now. So when we ask, quote 10, we should acknowledge that we might not even know what the worst case is. We can imagine large impactors, rogue planets, exotic compositions. But there might be scenarios we haven't thought of because we lack the imagination or knowledge to conceive of them. This uncertainty is not cause for anxiety but for wonder. The universe is full of surprises, and while some might be threatening, others will be enlightening and beautiful. The same cosmos that occasionally sends dangerous objects our way also creates stars, planets, the conditions for life, and conscious beings capable of understanding it all. Perhaps the real answer to our central question, what's the worst case scenario, is not a specific impact scenario, but rather the scenario where we let fear of cosmic threats diminish our appreciation for cosmic beauty. The universe is dangerous, yes, but it's also magnificent. The same processes that create potential impactors also create the elements in our bodies, the energy that powers our world, the structures we study and marvel at. We're made of star stuff, as Carl Sagan famously said. The atoms in our bodies were forged in dying stars scattered through space and eventually incorporated into the cloud that formed our solar system. We're recycled cosmic material, given temporary consciousness to observe and understand the universe that created us. Interstellar objects are our distant relatives in a sense. They're made of the same stuff, governed by the same laws, part of the same cosmic story. When 2I/Borisov passed through our solar system, it was a kind of homecoming, a piece of the galaxy returning to visit one of its children. This poetic perspective doesn't change the mathematics of impact probability, but it does change how we feel about it. Instead of seeing the universe as hostile, we can see it as indifferent but beautiful, dangerous but not malevolent. We can appreciate both the threat and the wonder, holding them in our minds simultaneously without contradiction. And perhaps that's the real skill we need to cultivate, not just for cosmic threats, but for life in general. The ability to acknowledge danger without being paralysed by fear, to prepare sensibly while still enjoying the present, to understand our vulnerability while still finding meaning and beauty in existence. The cosmos will do what it will. Objects will drift through space according to the laws of physics. Some will pass near Earth, and very, very rarely, one might even strike us. But we are here now, conscious and curious, capable of understanding these processes and perhaps even affecting them. That capability, that consciousness, is itself a kind of miracle, as improbable as any cosmic event. So yes, the worst-case scenario is possible. The universe could align against us. But it probably won't. The mathematics are on our side, the vast distances protect us, and in the meantime, we have this moment, this awareness, this opportunity to understand and appreciate the universe that contains us. Thank you for staying with me through this entire journey. We've been together for over 2 hours now, drifting through questions of cosmic danger and statistical grace, through the mathematics of impact and the philosophy of existence. That's no small investment of time, and I'm grateful you chose to spend it here. We've travelled together from the discovery of 2I/Borisov and Oumuamua, those strange visitors from distant stars, through the physics of impact and the challenges of planetary defence, and finally to the bigger questions of meaning and perspective that cosmic threats evoke. From the particular to the universal, from the technical to the philosophical. The question we started with, what's the worst-case scenario for Earth from an interstellar object, has received an honest answer. The worst case is truly catastrophic. A rogue planet or massive object striking at interstellar velocities, reshaping or destroying our world entirely. But the probability of such an event is so vanishingly small that it's almost not worth calculating. We're talking about timescales of billions of years, events so rare they might never occur during humanity's existence. The more likely scenarios, smaller impactors, the kind we might actually encounter on human timescales, range from negligible to devastating depending on size and impact location, but even these are extremely improbable. The universe has offered us a remarkable gift, a planet protected not by walls or shields, but by the sheer vastness of space itself. If you enjoyed this slow drift through cosmic questions, I hope you'll consider leaving a like. If you're not yet subscribed and would like more of these gentle explorations of science and space, please do subscribe. And I'd love to hear your thoughts in the comments. What do you find most fascinating about interstellar objects? Does thinking about cosmic threats change how you see Earth? Share your perspective. Wherever you are in the world right now, perhaps in bed as the day ends, perhaps in a quiet corner watching the night deepen, perhaps somewhere I can't even imagine. I hope you're comfortable. I hope your breathing has slowed, become deeper and more regular. I hope your shoulders have dropped. The tension leaving your body gradually over these past couple of hours. I hope your thoughts have quieted, the urgencies of the day fading into something more peaceful. Look up at the stars if you can see them from where you are, or imagine them if you can't. Those distant suns, each perhaps with planets, each perhaps sending objects into the void just as our sun does. Think about those wandering rocks and ice balls, those ambassadors from distant worlds, drifting through the darkness at unimaginable speeds. One of them might be heading our way right now. Statistically, several probably are. But space is so vast and Earth is so small that they'll almost certainly miss us. They'll pass by, perhaps close enough to be detected and studied, perhaps too far away to notice at all. And they'll continue on their lonely journeys through the galaxy, carrying their secrets with them. There's something beautiful in that, in the cosmic dance that brings these objects near us without striking us, in the mathematical protection that keeps Earth safe while still allowing these glimpses of the wider universe. We live in a dangerous cosmos, but one that, through its very size and emptiness, provides its own kind of shelter. The answer to our question, as honestly as I can give it, is this. Yes, the worst-case scenario is theoretically possible. The universe could align against us in ways that would end our civilization, or even our species, but it probably won't. The numbers are overwhelmingly in our favour. We're protected by probability, by distance, by the fundamental structure of space itself. And while we can't control the cosmos, we can control our response. We can build better detection systems. We can develop deflection capabilities. We can cooperate across borders. We can prepare sensibly while living fully. We can face the universe not with fear but with understanding, not with resignation but with appropriate confidence. Most importantly, we can hold both the danger and the beauty in our minds simultaneously. We can acknowledge that we live in a universe capable of creating and destroying, threatening and nurturing. We can feel small before cosmic scales while still feeling significant, vulnerable while still feeling safe, temporary while still feeling meaningful. Sleep well tonight. Dream of distant stars, of wandering comets, of the slow dance of gravity that keeps everything in its place while allowing everything to move. Dream of a universe vast enough to contain countless wonders and rare enough in its dangers that Earth continues its patient orbit day after day, year after year, millennium after millennium. Good night. Thank you for exploring these questions with me. May your rest be deep and peaceful, and may you wake tomorrow with a renewed appreciation for this small, beautiful, statistically protected world we call home. Good night.